All right, after much ado, let's get started here. Thanks for everybody for holding on, and the large group of people, I imagine we're sitting in the waiting room there and online. I appreciate your patience and your guys' patience, of course, sitting in here. Now the focus really, we've been shifting we're talking about absolute measures of performance. Now we're talking about relative measures of performance, which is really important for things like your final project, where now you want to compare, say, a baseline case to an intervention. So you might want to say, for my final project, I noticed that this particular restaurant operates in a certain way. I would like to make a major change in the way they operate. So instead of doing things first in, first out, I'm going to do things last in, first out, or something like that. And then you want to compare, did I make an improvement over that baseline case? And so that's a relative measure there. So it's a lot of times relative measures are easier to estimate than absolute measures, because absolute measures, they have to kind of be matched to reality, whereas relative measures, two relative simulations, they might differ, and one's better than the other. That difference might match the real world, even if the absolute measures don't. And so we'll talk more about that. Basically, assignments moving forward, there's an ICAL, which is available. And I think it'll be actually due the next lecture. I'd have to look, it might be due the lecture after that. We had to drop a lecture this semester because November 11th fell on a Thursday. And I don't remember if I was clever enough to update, and that lecture kind of combined L and K2 together. And I don't remember if I was clever enough to update this due date. So it's due whenever it's due, but this is the last kind of new ICA. And then ICA-M is another one of those study ICAs that is meant to be a study for the final exam. So it's a longer ICA. So instead of being 10 points, it's somewhere around 30 points. It takes a random sample of the post-midterm ICAs and maybe adds in a couple of other extra questions. Can be taken multiple times, and the highest grade is used. After the review day, which is lecture M, then ICA M goes away, but a practice version goes in place. And so you can find ICA M and the practice version of itself, as well as a practice version of the pre-midterm ICA, or the kind of a copy of the ICA you did before the midterm, all in the final exam module. And you'll need to take that compliance test for the final exam to show that your lockdown browser works in order to get access to that final exam module. But once you do that, then that final exam module's got all of these ICAs. It's got a bunch of sample final exams from previous semesters, and other resources. So make sure to do that to check those things out. Other assignments, homework J2 has been out there. I know somebody emailed me this morning with a J2 question, and I'll get to that this afternoon. Basically, this is the inventory management problem with Bucky that you saw before in one of the previous labs. I forget which lab it was. I think it was maybe lab 5 or 6. And but you're going to make a couple of small modifications to it, and then you're going to run an optimization on it. So you're basically going to say, all right, now that we've made these modifications, what is of these decision variables, little s and big S, then what's kind of the optimum combination for this setting? And you can do that manually, is fine. If you'd like to use the process analyzer or OptQuest, that's also fine. So those are kind of introduced in the lab. The only other lab that's left is lab 10. This is a little bit of a special lab in that it's a 30-point lab, but 50 points are possible. So it's almost like it's got another whole lab added onto it, an extra credit. And so the first part of the lab describes how to use these things called sequences, which are these really cool things that help simplify routing in Arena. And the second part describes batching, signaling, and holding. Both of these could be very useful when you're building complex models in Arena, which is why I wanted to make sure you saw them. So if you want to do both of them, you can, and you can potentially score up to 50 points. Again, there's a drop 2 lab policy as well. So some of you may say that I don't really want to worry about lab 10, but for those of you who want to score a couple of extra bonus points, this is sort of one of the last opportunities to score bonus points in the class, in that you've got this extra kind of lab bolted onto it. So something to think about there. After that, all the rest of the time left in the semester that would normally be for labs, you can view as kind of open time for working on your final project modeling. And so if you're having any particular difficulties, feel free to reach out to me. Just so everybody knows, so I've had office hours kind of by appointment this semester, and people have been making appointments with me. And so if you haven't done that, feel free to reach out. I have a decent amount of availability through the week. As long as even sometimes if it's that day, but usually I need kind of a day ahead of time to kind of figure things out. But please feel free if you want to say like, yeah, we're not quite sure how to model this particular aspect. You have some ideas, I'd be happy to meet with you and sort of talk some of those things out. Or if you just want to send me an email, I can maybe send you like, oh, by the way, chapter 16 in the lab textbook has a good section on this, check that out. We can do that as well. So please don't be shy. I am definitely happy to help. Otherwise, yeah, so final project stuff, just general questions as you're doing it. So all of you have got your feedback back on your input modeling reports, both annotations written up as well as comments within the rubrics. So if you haven't taken a look at that, please do. The biggest thing that you really just want to make sure of moving forward is, have you picked kind of a sufficiently complex kind of question to ask, as well as kind of a sufficiently complex simulation model to use. And so the big thing here is, do I need a simulation to really answer this question? So if you're really asking a question that you could go into 470 and use a simple queuing model to do, and you know, and maybe as a homework problem, you'd have an answer, you know, in a half hour or something like that, then maybe that's not something that's appropriate for simulation. But if it gets to the point where you're like, wow, you know, I don't even know a mathematical framework where I could start with this, then that's kind of where sim comes into play. And so you kind of want to make sure that you've kind of made things complex enough that we don't have another stand-in. Now, I don't want you to be too ambitious, but a lot of times adding real world complexities, you add one or two, and you're already in the point where a sim is really the most appropriate tool. So it doesn't have to get too crazy, but we want to at least be something that a lot of times, when I used to have people present in class, I'd have some of the other IE faculty come, and they'd sit, you know, in the row, and they'd ask their questions to the students, and that was frequently a question like, well, what other way could you have used to solve this? And then the students would be sort of like they'd freeze up, because they'd be like, oh, that's my 470 professor, and he's asking me how could I use 470 stuff to do the same thing, you know? And that was always kind of the frequent sort of criticism from, you know, other faculty, is like, well, couldn't you have used something else? Like, why did you have to use simulation? So that's kind of the big thing to look against. We used to have this requirement that which isn't a formal requirement anymore, but we wanted the models to be complex enough that you used a sub-model. So in Arena, you can highlight a bunch of blocks and you can hide them behind a single block called a sub-model. And if it was sort of complex enough that you needed a sub-model, then that was usually a good heuristic to tell you that it was probably complex enough to warrant simulation. So in other words, you don't want it to look like an MM1Q, because it's, in that case, it's only got like 3 blocks in it. But, you know, if it looked kind of like this sort of system with like 5 blocks, another 6 blocks, another 3 blocks, and you could kind of bundle each one of those into subsystems, well, then maybe it was kind of complex enough that mathematical analysis wouldn't be warranted. But the kind of bigger point is really, why is simulation necessary to study this problem? Why did you have to build a model and simulate it and not build a model and analyze it in other ways? So just keep that in the back of your mind as you're moving forward. And but also make sure you have a feasible, so don't, you know, like if you've got 12 decision variables, maybe think about 2 decision variables, you know, like, you know, similar to, if we go back to the homework J2, you know, that's a relatively sophisticated inventory problem with 2 decision variables. So homework J2, that kind of is a nice model for a type of thing you'd expect on your final project. It's a relatively complex system. It's got several blocks, things running in parallel. It's not really clear how you'd solve it without the sim. So yeah, you could use something like homework J2 as a model for the model that you're trying to build, like something similar in complexity to homework J2. Otherwise, the presentations last week of class, the Wednesday of the last week of class, Wednesday night. So 10-minute is a hard limit on your presentation. If you want to go under that, nobody has ever complained about a presentation that was too short. It's always good to be short. on presentations, just so long as it's complete. So it needs to tell a full story, but you're not going to get any points off for running 9 minutes. Or, if you run 8 minutes or 7 minutes or 6 minutes, you have to ask yourself, well, did I leave something important out? You don't want to leave people with a lot of questions like that, like unanswered. You want them to be interested enough to ask questions, but not like, wait, so what did you do? So you really want to make sure that you sort of motivate the problem, present the basic points of your model and how you solved it, and the basic results, and then draw discussions or conclusions from it. So as long as you kind of do the intro, the methods, results, and discussion, if you've got all 4 of those parts, it could be 8 minutes, and that's fine, and nobody's going to care. That they'll probably be happier that it's 8 minutes than 10. If you go a little bit over, like 10 minutes and 10 seconds, don't worry about that. But you really want to say, like, you really don't want to go. Like I say, it's a hard limit, but it's not like I'm not going to take off points for every second over 10 minutes you go. But I would say that you're not going to be able to count on your listener watching past 10 minutes. So if you were to give it to me, if I've watched it for 10 minutes and then something else comes up, like I've guaranteed I'll give you 10 minutes of attention, just like you're giving me, and I'm very grateful for your 75 minutes of attention every twice a week. I'm going to give you, 10 minutes of attention for the presentation. And likewise, your peers will give you 10 minutes of their attention. You can't count on them watching any farther than 10 minutes. So if you want them to score you, make sure you put the scoreable stuff in the 10 minutes. That's all I'm saying about the 10 minutes. And then, so like I said, your peers, your presentation will be assigned to probably 4 or so of your peers randomly. And so they will then fill out a rubric, and I will see all those scores and aggregate them with my scores to determine your presentation, similar to your final report. Your final report has got a 4-page format that is detailed online. Stick to that format, that's part of the rubric. You can see the rubrics for both of these that are online. And then likewise, your report will be assigned to about 4 people randomly, and then they'll read it through that, and then they'll also fill out that rubric, and we'll aggregate all those scores. I see a question online. There's a question about the presentation online. Can we just overlay our voices on the PowerPoint, or would you like a recording of us talking with a projector or something? The format of your presentation is up to you. If you feel you'd be most comfortable just overlaying your voices on top of a PowerPoint, you feel like that's the most effective way to present the material, that's fine. Now that we've been kind of Zoomified, I think you find that Zoom screen recording capabilities allow for a lot of other really interesting things you could do. Like, for example, you could switch between PowerPoint and your Arena model. You could actually run the simulation during the presentation. Or, I mean, in Arena, you can capture videos of your presentation and embed them into your presentation. So that's fine too. But it's sort of up to you exactly the format of how you want to put things together and how you want to record it. You don't necessarily have to use all of your team members, like strictly, it's like, I'm not going to say like, oh, well, of the 10 minutes, they had 4 team members. And so it was 2.5, they split it up and everyone got exactly 2.5 minutes. I mean, really want to say in the rubric, I think it's most effective use of the team. Well, sometimes the most effective use of the team isn't for all 4 people to spend exactly 2.5 minutes. I want it to be clear across your deliverables that all of your team members participated in a useful way, like that they were in an invaluable way. But I don't necessarily think that, like with any presentation, that the presentation has to be divided equally across the team members. Like in the real world, that's not how it would happen, right? So you probably would swap off between expertise to make sure you've got the best person talking about the best things. But it wouldn't necessarily mean that every single person on your team is going to give that presentation to the larger group in the office or something. So things to keep in mind. So I hope that answers the question. Totally fine with overlays on top of the PowerPoint if you feel like that, but a lot of other recording options possible, especially with Zoom. You just go into Zoom, you could start a little room with all of you. You don't even have to be in the same physical space, and one person could be sharing their screen and the other person could be talking. That's fine too, whatever you would like. Any other questions about this sort of stuff, presentation format or structure or anything like that? Okay. All right. Any other questions about the general admin stuff? Pretty clear schedule going forward. I think given that we've got not a lot of Thursdays off this semester, so we've got this Thursday we'll have a lecture, Tuesday we'll have a lecture, then Thanksgiving's off, and then after that, that's I think the last week of classes. And so come back from Thanksgiving break, that's the last week of classes. We'll have the review lecture for the final exam. Your stuff will be due Wednesday of that week, and then Thursday we'll have stage 1 of the final exam, and then I forget which day during the finals week we're assigned, but I think it's Tuesday, but it's on the calendar. Then you'll have stage 2. So there's not a whole lot of runway left. So we're about done. All right, so let's do a quick attendance exercise. And so I'll put the link in the chat. And so go ahead and put down in your under the link what you think this is. And so a point estimate is equivalent to what type of confidence interval. So a confidence interval degenerates into a point estimate under certain values of confidence. And so the question here is it a 0%, a 95%, or 100% confidence interval, or is it or a point estimate significantly different from a CI? So go ahead and put down what you think. And then after that, those who are online, if you'd like to just share your answers in the chat, and then I'll kind of do a little poll here in class. How many people think it is D? How many people think it is C? How many people think it is B? How many people think it is A? All right, so we got kind of a split in the class between B and A. And so far online, I see also another split between B and A. And so I guess it's definitely good that C and D didn't come up here. I guess I can understand why it would be a split between B and A, because we talk so much about B, but we've also talked a little bit about what we mean by 0%. The answer that I would give would be A, that it would be a 0% confidence interval. The idea here is that the 0% confidence level, that means that your true negative rate is 0%, or you could say your false positive rate is 100%. And so this is like setting your alpha equal to 1. And so a false positive rate of 100% would be like a confidence interval that's collapsed to a point where you're rejecting everything. And so the false positive rate is you're saying basically everything but this point, this single point on the real line is a rejection. So the only thing that we could possibly be is this single point, and everything else was a rejection. Well, now it's very unlikely that that single point estimate is the real value from the real world. And so most likely we're going to be rejecting the right thing. So a 0%, a point estimate is when you have you have actually zero confidence that you captured the real thing in the interval. 100% confidence interval means you have 100% confidence that the interval captures the real thing. And so 100% confidence interval is the whole real line. So we kind of balance, and so we typically in science settle on a 95% confidence interval, which is an interval that because it's less than 100, it is not the whole real line, but we don't collapse it all the way to 0 because that's not a good thing there. So this 5% going from 100% to 95 is enough to collapse it to usually a usable region where the things in between is kind of sufficiently narrow that we can kind of say, well, we know the real one is probably inside there, and we know there's a lot of things that we've excluded. So the confidence interval is more about what you exclude than what you include in the interval, and the 95% usually excludes a lot and leaves us, the rest in the interval is just the ambiguity of where the real thing that we're trying to estimate is left over. And so so that's kind of it. So any questions about that? Is that clear that a point estimate, if you just give a number, you say, I think the average age of all people in the United States is 46.72 or something like that. Then that, if you just give that as the average age based on sampling 1,000 people and asking what their ages are, you're most likely going to be wrong. So that point estimate itself is a 0% confidence interval. The real age is not in the interval. But if you give a confidence interval around it, I actually think it's somewhere between 40 and 45. Then the real average across the whole United States population is probably in there. And how often it's in there is kind of the confidence level here. So 95% of the time it will be in the interval. That's the way we interpret this. So a 0% means that it will never be the interval. That happens when it's collapsed to a point. 100% means it's always in the interval. That happens when it's the whole real line. 95 is the balance in between. Okay. All right, so another one here. Let's do this, the second attendance exercise, right in a line here. And so the question here is, assuming we have similar estimates of standard deviation from a population, across these three intervals, so all these intervals were calculated with the same estimate of standard deviation, which of the three intervals corresponds to the largest number of samples? And so the only thing that's differing from one interval to another is how many samples were taken of the population. So really what I'm asking here is what happens to confidence intervals as you take more samples? Do they get larger or do they get smaller? And so if I want to say here is which confidence interval has the largest number of samples, I'm effectively asking you really what the difference between B and C. So if I took a large number of samples, did my confidence interval get really small or did it get really big? So go ahead and put your answer into the attendance exercise. And then the same thing online. So looks like some people already answered it. So you can go ahead online and put your answer in the chat. And then in the room, I'll ask, how many people think the answer is A? How many people think B? A lot of hands for B. How many people think C? All right, good. So everybody says B. And that's good. That's what I was looking for. As you take more samples, your 95% confidence interval gets narrower and narrower, and that you exclude more values outside the confidence interval. So the increase in predictive power that you get manifests itself as a smaller and smaller and smaller interval. It gradually collapses. And so if in the 1800s, when the only statistics they had were large number statistics, where they took lots and lots and lots of samples, they could get away with that because they sampled so much that if they use small sample methods like we use, their confidence intervals would be like a point. They wouldn't collapse so far that they'd effectively be a point. And so in the 1800s, when they're going, doing stats on fields, and they've got, 1,000 plants or whatever, then when they're doing those stats, if they did happen to take an average of those sorts of numbers, then that point estimate may as well be the confidence interval, because confidence interval, even at 95%, collapses to a really small number around that. We are trying to be a little more economical with our statistical methods. We don't want to run 1 million replications of that stupid call center. We only want to run 10 replications of the call center. But by running 10 replications, then we don't have as narrow of our confidence intervals. But as long as it's within our sensitivity constraints, then we're okay. So that's good. So everybody got the answer that I was looking for. All right, so just to kind of summarize all of that, a confidence interval is a graphical summary of a t-test. And so if I take the conditions for, in this case, this is the conditions for rejecting a hypothesis by a t-test up here. See if this guy works up here. Then these conditions up here are equivalent to the conditions of the hypothesis that you're testing, theta, down here. That hypothesis, if it's rejected, then that is equivalent to saying it is outside of the corresponding confidence interval. Down here, if a hypothesis is not rejected, that's the conditions down here for a t-test, that is equivalent to saying that the hypothesis is in the confidence interval over here. And so that is and likewise, it's equivalent to saying that if you ran the t-test for this top condition, the p-value would be less than alpha. If you ran the t-test for this bottom condition, the p-value would be greater than or equal to alpha. So that half-width there has that critical t-value in it because it's just a rearrangement of these conditions. So that's where you get that. And so in your head, eventually you should burn into your brain that a half-width is just the standard error of the mean scaled by the critical t-value for a two-sided t-test. That's what a confidence interval is. So just, you know, right now it just looks like a formula, but over time, eventually you'll feel that viscerally, that a confidence interval half-width is just standard error of the mean times critical t-value. That's all it is. All right, so with that confidence interval, we have a bunch of heuristics that we can apply when we look at data. So like I was saying, if a 95% confidence interval does not include the hypothetical mean, the hypothesis is rejected. And so this is just kind of summarizing all of that. So the way I view that is if I run 100 experiments, and so that's what I've got summarized here, 100 experiments on top, I've got 100 experiments in the middle, 100 experiments on the bottom. The difference between the top, middle, and bottom is at the top, I have 20 samples in my experiment. So each experiment summarized by a confidence interval is only 20 samples. In the middle, it's 200 samples. In the bottom, it is 2,000 samples. And so across all of these things, as I see that as I run more samples in an experiment, the confidence intervals get narrower. But across all of these things, regardless of how many samples I run per experiment, if I run 100 experiments, roughly 5% of them don't include the mean that I'm actually trying to estimate by running those experiments. And so, so 95% of them roughly capture the true mean, but 5% don't. So this just goes to show that you shouldn't ever report a point estimate, because look at the huge variance in point estimates. That's the middle of these confidence intervals. From experiment to experiment, you get a lot of variance across. So again, if I do the age example, if I take 100 people and take their average age, I'm gonna get a point estimate. If I take another 100 people, get their average age, I'll get another estimate, and so on and so forth. From 100 people to 100 people to 100 people, that point estimate is gonna vary a lot. But if I put a confidence interval on one of those groups, then just doing it once, I'm pretty sure the real age is in that confidence interval. I don't have to then do it again and again and again and again. So with just 100 people, I can be pretty confident that I know the range of where the true age is. And so that's where we have the confidence interval. When I pay my mortgage every month, my bank gives me an opportunity because they want me to refinance, they want me to buy a new house or whatever, and they tell me what the value of my house is, and they always give me a low end and an upper end. What they're doing without saying it is giving me a 95% confidence interval. They're saying that if you were to put your house up for sale today, I don't know exactly what it will sell for, but I am 95% confident it will be within this range. And that number, their accounting people did effectively this, but they did it based on other houses. So based on other houses similar to my house, we sampled what they sold for, we took their average, we put a confidence interval around it, and then that is where your house will sell. So that's how you should view confidence intervals. All right, so similarly with confidence intervals, if I get more variance, so top, middle, bottom, this is a population that has a lot of variance. So in the house example, this is, has not very much variance. So in this house example, if they found 100 houses that were like mine, and they all sold for roughly the same thing, they generate this confidence interval. Down here, a lot of variance. If they found 100 houses that were like mine, but they found there's a huge variance of what they sold for, then this would be the confidence intervals. And so the bank here would be pretty confident what my house would sell for. Here, they would be not as confident what my house would sell for. And it all comes from the variance in the population. We, as simulation designers, as we'll learn about in the next lecture, actually can control some of this variance by cleverly designing our experiments. And so we have the ability to control variance as well as number of samples. And so that's kind of the two things I'm saying here. More samples is one way you collapse these confidence intervals. Less variance is another way you collapse these intervals. All right. Now, so regression lines. So you guys all have learned a little bit about linear regression from whatever 380 or 385. There is a p-value that's associated with a regression line. So when your p-value within a regression line is less than 0.05, does anybody know what that means? So, you get you run a regression line and you get a p-value out. So you get something like this, and it gives you a regression coefficient that comes out of it and an associated p-value. And so the question is, a p-value means that they're testing against some hypothesis. What is the null hypothesis for linear regression? Does anybody know? Online too, if anybody has an idea for that, you can put it in the chat. What is the null hypothesis for linear regression? And you can think of it in terms of slope. What is the null hypothesis of a slope? You're saying, I think the thing on the x-axis is related to the thing on the y-axis. I think, and I'm going to plot this thing and run a linear regression on it. What would the null hypothesis be if you've got a thing that you think is related to something else? What's the null hypothesis? Any thoughts? So there's a comment in the chat about it tends to be linear. So yeah, linear regression looks for linear relationships. And so, but the null hypothesis about those linear relationships is what? Any guesses, thoughts? So, I mean, you think about it, the null hypothesis, when you have two things that you think are related, is that they're not related. So these things might be related. And if they're not related, then you'd get a flat relationship here. So across all values of your x-axis, you would get no relationship to values on the y-axis. And so you just get a cloud of points that would be scattered, peppered in a horizontal way across here. So effectively, the null hypothesis is these things aren't related. And so the regression coefficient, which you can relate to the slope of the best fit line, the null hypothesis on the regression coefficient is that it is 0. So if it has 0 slope, then these two things aren't related. So when we generate a linear regression and we generate a regression coefficient, or the related quantity, a slope on this regression line, we can then start to say that we can run t-tests on these slopes, and then we can also put confidence intervals around these slopes. And so what we really want to know is, all right, I estimated a slope there. Well, if I get a bunch of points, I'm going to estimate some slope, and it's probably never going to be exactly 0. But then I can ask the question, can I reject 0 as a plausible estimate for that slope based on the data that I get? And so that's where we actually put confidence intervals around regression coefficients or around these slopes. And so this is a paper from a colleague of mine, and the details don't really matter, but just happened to grab this because this was an easy example. And she studies in ant colonies how, if you look at how massive the colony is, so you could have 100 ants or could have 1 million ants, you can then actually then hook up a gas setup, a respirometry setup, just like you would if you were like, doing high performance sports or something like that, where you could you put something on your mask and you can measure CO2 production. Well, you can measure the CO2 production out of an ant colony based on how big it is. And what you find is that the bigger colonies produce more CO2, which makes sense. But there's a big question about as the colonies scale, then how much more CO2 do they produce? Does it scale linearly, or does it scale with some other exponent? And so she's got these data here, and it shows that, yeah, it looks like there's a relationship here. So she fit a line here, and this line has a point estimate of its slope of 0.7845. So it looks about like 3/4 here. But in the paper, she says that they had a scaling relationship to the 0.78 power. The reason she says power is because this is on a log-log scale. But we don't have to worry about that. The point is here, she's talking about that slope there is 0.78. But then she gives the 95% confidence interval of the slope. And she says it's between 0.671 and 0.898. And so this right here, the key point that we need to take from this is that this confidence interval does not include 1.0. So what we're saying here is that we are rejecting the hypothesis of linear scaling here. So this means that as this organism, as this colony gets larger, if it doubles in size, it doesn't double in energy expenditure. And so this is what we call hypometric scaling. It scales under linear, sublinear scaling. And so they've rejected 1.0. It doesn't show up in this confidence interval. If she were to run this experiment again, she would have got a slightly different line, and again, a slightly different line. But we're pretty confident that if she ran 100 of these experiments, that 95 of them would include the real slope, and it would very likely not be 1.0. So 1.0 is probably not the real slope. So then she goes on and says, this scaling exponent is statistically less than 1. That's her saying that 1.0 is not in the confidence interval and is not statistically different from 0.75. You see, there is a theoretical prediction here that, so based on math, without any stats, there's some math that suggests that these things should scale with a 3/4 exponent. So there is some math out there based on some assumptions of how physiology works, that this should be 3/4. And so what she's saying is that, look, when we took data, 3/4 is inside our confidence interval. Yeah, it's not the point estimate, but it is one of the possibilities that we're including here. And so that right there means that we are not rejecting the theory. The theory seems to be consistent with our data so far. So they rejected the naive case of isometric scaling. They have implicitly rejected no relationship. That would be 0, because 0 is way outside of that confidence interval. And the things left in the confidence intervals represent potential theories that could still work, like the 0.75. So as this is why I want you to get more comfortable with confidence intervals. They show up everywhere. Linear regression itself, the regression coefficients, you put confidence intervals on, because the coefficient itself is a point estimate, and no one likes point estimates because point estimates don't tell you anything. So then you say, well, that slope is just a random chance slope. What's really the bounds on what the real slope might be? That's what these are. So the real slope is probably from 0.67 to 0.898. The real slope is probably not 0, it's probably not 1, but it's somewhere in between here. So confidence intervals on regression coefficients. That's kind of an important thing there. All right, any questions about this example? Confidence intervals on regression coefficients. And this is text from the paper where they list the confidence intervals right in the text. That is a common way to do it. People look for confidence intervals. They're so informative. All right, another example here. This is from another colleague in Pennsylvania. I do a lot of work with ants. I do a lot of bio-inspired work. So I build algorithms which are based on things that go on in ant colonies, and my algorithms run smart buildings and things like that. And so, but I also work directly with ants, and so that's why a lot of these happen to be ant examples, because they're the papers that are just pop into my mind quickly, and I think it's kind of fun to have science examples. And so Tim, in this paper here, what he was measuring here doesn't really matter, but what he's trying to say here is that he's measured these different traits, and he wants to show that that some of these traits potentially have a relationship to those traits in a previous generation, and some of them do not. And so rather than even showing a t-test results, p-values or whatever, what he's done is he's shown the point estimates here, and then the confidence intervals next to it. And these confidence intervals, if they include 0, then we have not rejected the null hypothesis. And if they don't include 0, then we've rejected the null hypothesis. And so this little asterisk down here, 95% confidence intervals do not include 0. He doesn't even say what that means. He just counts on the reader knowing that what he's saying here is that these 3 confidence intervals, because they do not include 0, they are a statistically significant difference from 0. So this is the language that people use out there in real statistics there. Sometimes they formally say, that P is less than 0.05. But a lot of other times when data are summarized, they just say confidence interval does not include 0. And you have to know, what does that mean? Well, that means that 0 has been rejected. P is less than 0.05 for the hypothesis of 0. So just listing confidence intervals is a way you can communicate that. And all right, so any questions about these examples here? So just trying to bring confidence intervals meeting linear regression. This is basically regression coefficients here, saying the regression coefficient's different from 0. This is saying the regression coefficient's different from 0 and different from 1, and includes the theoretical expectation as well. So a lot of very rich data in this set. Okay. All right. So now so what we're moving towards here is how to compare. So these are all absolute metrics. So this is like, what is the regression coefficient for this relationship? Now, what we like to really do is be able to compare two populations. Simulation A, baseline, versus simulation B, intervention. And so, how do we do that? Well, one way we can do that is with a two-sample t-test, which if you have the confidence intervals for simulation A and the confidence intervals for simulation B, then sometimes you can make an inference immediately just by calculating this. So you could run ARENA, grab the confidence interval out of the reports tool and just write it down, and then rerun ARENA for your other model, grab the confidence interval out of the reports tool and write it down, and then ask, do those two confidence intervals overlap? And if they do not overlap, so there's no intersection between them, then in that case, you can conclude without running any t-tests that your two simulation models have statistically different results. So that maybe your baseline model is actually poorer performance than your intervention. And so you're good without even running another test. So if the one sample confidence intervals, so the absolute confidence intervals you get by just running one and then the other, are disjoint, then you can reject the null hypothesis that they're equal and conclude that they're not equal. But if they overlap, so you run model A, you run model B, model A's confidence interval in ARENA's reports overlaps model B's confidence interval in reports, in that case, you have to do more work. You actually have to do the two-sample t-test. So in that case, you got to dump the data into a DAT file. You got to dump the other data into a DAT file. You got to go into the output analyzer. You got to load both of them up, and then you've got to do a two-sample comparison of the means and have it do a formal t-test. Or you have to go into JUMP and take all the data out of the one model, all the data out of the other model, put it into a two-sample t-test in JUMP, and have it run that two-sample t-test and see what the p-value is. So, but if they don't overlap, you don't even have to do any of that. You can just jump straight to the result. If they do overlap, then you actually have to, run JUMP or run the output analyzer. So, so there are shortcuts here. So if you were to plot your confidence intervals for model A or model B, in this case, it's HIV detection method A, HIV detection method B. Here, these are confidence intervals, 95% confidence intervals. And in this case, they overlap. So you might conclude that there's no difference between these populations, but when you actually run the two-sample t-test, you find that it is less than 0.05. And so if the confidence intervals overlap, it's still possible that the t-test will reject the null hypothesis that these are equal and conclude that they're different. So sadly, if they overlap, you have to do more work. But if they don't overlap, you're done. You can just, at least when you only have two models, baseline and intervention. So you can think of this as like control and treatment. Okay, now what we're going to be moving into now today is, well, how do we build a confidence interval that gives us the same sort of intuition as for a one sample test for these two sample cases? And so I was just talking about how you could run a one sample absolute confidence interval for one model, a one sample absolute confidence interval with a second model, and compare the confidence intervals. When we can't do that, we still would like to graphically summarize the two sample t-test results, because it tells us a lot more rich information. And that's what we're going to be talking about today, is how you turn two sample t-tests into a confidence interval, where that confidence interval is actually a representation of the difference between the two systems. And if that difference overlaps with 0, then we can't conclude anything about the two systems. But if the difference does not overlap with 0, we can conclude that one system has a larger performance measure than the other. So that's what we're getting into here. How do we build these 2 sample confidence intervals? All right. So, so any questions about any of this stuff, this general ideas of, you know, how we look at confidence intervals and interpret them as summaries of these different types of tests? Any reflections on this? Okay. All right, so far we've talked about transient simulations, and we need to figure out how many replications to run. We talked about from like homework G3, you could use a formal power analysis, but oftentimes it's more convenient or quicker to do this kind of confidence interval approach instead, where like we did in lab 9, then the idea here for lab 9 here was that I give you a narrowness requirement for the half width. And then if you say, I need to run enough replications that my half width is within this sensitivity bound, then you can run a pilot experiment. And then from that pilot experiment, figure out how many more replications you need to bring the half width down, run those. And then if your half width is within the constraint, then you're done. And so this bound on the half width is kind of a convenient way to get at something very similar to power without formally having to calculate power. So this is kind of the way that it's a very practical way to do things, especially in simulation. So the way we do that is you design your replications to be independent. Normality often holds. And then from there, as long as you've got independence and normality across your replications, choose a pilot number of replications R naught to generate an estimate S naught of the variance, and that S naught of the variance there ends up being plugged into this formula down here. And so you've got the z-score, the critical z value for alpha divided by 2. So in this case, if it was for 95%, this alpha divided by 2 would be 0.025. This would be 5% divided by 2. You look up whatever that value is there, multiply it by the variance estimate, divide it by the half width constraint, square that ratio, and that tells you an estimate of how many replications you need to meet that half width constraint. So once you have that, you've already run R naught replications, so you just run whatever the balance is, and then pool all those together, and then hopefully that will be within the epsilon half width. And if it's not, you run a few more replications until it is, but this is at least get you in the ballpark. So that's kind of the simple way to choose how many replications. And you can do this for your final project too. You can say, I've got a performance thing, and really as long as I estimate it within, you know, a minute. So if I'm estimating what's the average wait time for a customer at this restaurant, as long as I estimate it, you know, a confidence interval within a minute, then I'm gonna be okay with that. Well, that's your epsilon, a minute. And so now you can run a couple of simulations and you find out that that gives you your variance estimate on the average wait time. And then from there, you can say, well, how many more replications do I need in order to get my estimate of the average wait time down to where the half width is a minute? And then you could then figure out, okay, I need 26 replications for that. Well, I run my 26 replications and there, lo and behold, I estimate the half width within a minute, and that is reasonable. So estimating the average wait time within 10 minutes is probably not reasonable. And so that's why we have these things. It increases the sensitivity of our model. All right, questions about this basic idea? You practice in lab 9. Okay. All right, so then when steady state simulations, they pose additional challenges that have to do with this bias. You've got this initial period that you don't care about. And if you accidentally include it, it's going to bias your steady state estimates. And so we either can do intelligent initialization, where we don't initialize everything at 0. We initialize them at something non-zero that's closer to the likely steady state. We do a warm-up period. So we choose a certain amount of data to throw away. And then we decide, do we run more replications or more execution time? And if we run more execution time, we reduce the bias, but we might have to run less replicates on our computational budget. So those are the things that we talked about last time that I'm going to summarize here, because we kind of truncated that there right at the end. And so we talked about that that basically all I'm kind of saying here is that if bias remains, adding replications is not going to get rid of the bias. It will always be there. So you really need to remove the bias before you add a bunch of replications. But once you get rid of your bias, then you may still need to choose a number of new replications. So, so there's always this balance here, where you're probably going to need to run more than one replication, but the smaller your replications are, the more bias you introduce. So there's general rules to try to figure out exactly how long your simulation needs to be. So if you, for example, decide that you're going to discard D data points, then the general rule is that you better have 10 times that after that data points. Or in the continuous time here, the rule is if you have an initialization period of T naught, you want your end time to be at least T naught. It's just a heuristic. It's not guaranteed for anything, but whatever you decide about your initialization period, you want to make sure you have that much more data. Now, once you've done that, then you choose your number of replications, and you want to choose it to be as high as possible. But if you choose more than 25 replications, at that point, you actually don't get a lot more benefit in terms of statistical power by generating more replications. So at the point where you think you might want 30 replications, take those extra computational time you would have put into 5 replications, and instead lengthen the 25 you've gotten. Because by lengthening the 25 you've gotten, you will actually reduce the variance in your steady state estimate. And I'll show you how to do that here. So the idea here is I've got an initialization phase and a data collection phase in my steady state simulation here. And so I'm going to truncate the initialization phase and only take data in the data collection phase. If I've decided that I ran R naught replications, but I want to run R replications total, then I can come up with this scale of R divided by R naught, which is how many more replications that I want to run. And I can scale my T naught, my initialization phase, up by that amount. And then I can also scale my total time up by that amount. If you do both of these scalings, make your initialization phase that much longer and make your data collection phase that much longer. If you do both of those, this will have the same bang for your buck in reducing variance and gaining statistical power as running more replications. But it has the additional benefit by reducing bias, because it throws away more of this ugly initialization stuff that biases your results, and it washes more of the residual bias out by having more data collection here. And that additional data collection is going to reduce variance in your steady state estimates. And that's what allows you to run longer replications instead of more replications. So that's the general rule there, is that try to always have 10 times as much data collected as discarded. If you need more than 25 replications, try to run as many replications as you can. But if you need more than 25 replications, then instead keep it at 25 replications and instead extend the length of your steady state simulations, because that will reduce your bias while also reducing your variance, so that you won't need more than 25 replications because the variance will get reduced. So that's the kind of steady state process for how you choose the length of the simulation and the number of replications. Is there any questions about that? Online as well. Is that clear, these differences here about what I mean by the number of replications and the length of the sim and how they might relate to each other? I mean, the big trick here is with a steady state estimate, I'm actually going to be sampling the data collection phase many, many times and averaging over that. So the one data point that I get from each replication is itself an average from many correlated data points within the replication. And that's the reason why extending the length of the data collection phase reduces the variance, which is why I can get away with extending the replications instead of generating more replications. And I have the additional benefit of getting rid of my bias. Okay. All right, then the other alternative we have, if we can run really long replications, is something that Arena tries to do for you automatically. And so if you run a really, really, really long simulation for a steady state simulation, you can discard your initialization phase, and then you can cut the rest of the really, really, really long data collection phase into batches. And if these batches are sufficiently long, then if you take a performance estimate from batch 1, it will not correlate with a performance estimate from batch 2, even though they're running in the same simulation. They just have, but you need to be really, really long here. So if these batches are small, then there's probably going to be high correlation between these, and you won't be able to do this. But if they're really long, then these will stop being correlated, and then one simulation run will end up generating a bunch of data points. And what's nice about that is there's only one initialization phase. Normally, if you run R replications, each replication needs a costly initialization phase where you run through all of these points and don't use them. And so rather than duplicating this waste R times, you only do it once and you run it one time. And over that one time, if it's long enough, you end up getting out R sample points as if you ran R replications. And so, like I said, Arena tries to do this for you. If you run a long enough replication in Arena, it will automatically divide up your data collection phase into these batches. And then it will look for correlations from batch to batch. And if it detects that there are no correlations from batch to batch, it will generate a confidence interval for you, even if you've only run one replication. Normally, you can't generate confidence intervals with one replication, but it does because it turns them into this kind of pseudo replication where it's generating replications from a single replication. This is the reason why if you look in the Arena reports, sometimes when you look at a performance measure, if it instead of a confidence interval, it'll say something like correlate. What that means is that you didn't run it long enough for this trick to work for Arena. And instead of generating a confidence interval for you, it says, I can't generate a confidence interval because those are correlated. They're not independent. And so that's something that you can look at as an alternative. And you can always try with Arena, making your replications longer and longer and longer until it generates a confidence interval. And that's an alternative then to running multiple replications. So that is another trick that is frequently used, the so-called batching trick, where you only have to pay the initialization cost once. So you might ask, well, how does Arena figure out what's long enough? There's actually tools where you can do this manually yourself. You can pull in data from one replication into the output analyzer, and the output analyzer has a parallelogram, and you can pull that in. And this gives you in what's called an autocorrelation plot. So every tick, and we've talked about these before, we're talking about for independence, every tick represents a distance between 2 points in a time series. And the correlation between that point and that point that's so many ticks away. And so what the blue here says that they're significantly correlated. And well, I guess the red is just negative, but there are boundaries that you can place across here. But as long as the blue and the red are inside those boundaries, then you can say that these points are not very correlated to each other. And so what Arena can do is it can look at your data series here and it can automatically put those boundaries on it. I think I have an example that I did in MATLAB. So MATLAB also has a parallelogram that you can pull up, and it's got the boundaries that it plots on there for you. And Arena can say that, oh, it looks like after 20 time units, you lose correlation. So we're going to create batches that are, say, 100 time units just to be safe, like 5 times more than that. And if you're 100 time units away, we're pretty sure that you restore independence. And that's a way that you can come up with your own batch size. So that's all I'm kind of saying here. But Arena does this automatically for you. So this is an option. But if you're wondering what's going on behind the scenes, this is what's going on behind the scenes. And Arena even gives you these tools to do this analysis for you. So you can look for these correlation links. Okay. All right. So any questions about that? So that's how to pick replications and how to pick replication lengths for steady state simulations. For transient simulations, you're stuck with the length. For steady state simulations, you choose the warm-up period and the total length. And if you choose them very long, that might have a consequence on how many replications you run as well. Does that make sense? Those basic principles. All right. All right, so let's get a little of this then under our belts here, and we'll finish this up next time as well. So we've been talking about output analysis for absolute one sample cases. So when you're just trying to estimate a single parameter, now we're talking about estimation for comparing systems together, where you don't actually care about the absolute numbers. You really just know is one system better than another. So an example you have here is sort of like a call center example where I've got two different hypothetical call centers. One of them might be the current call center, the other one might be a proposed change. The current call center, callers come in, they go through a selection, whether they want to go to billing or support. 41% go to billing, 59% go to support. I'm hoping you see all the input models here, like you would have to estimate these parameters in a decide block, and then how long do billing calls take, how long do support calls take. So you've got an activity duration here, an activity duration here, and then this kind of proportion here. All those you could estimate from data. Then so here you've specially trained billing operators just to do billing. Here you specially trained support operators just to do support. We primarily get support calls, not billing calls. That's why we have 4 operators instead of 3. But you might look at this and you'd say, but the utilization of my billing operators is still pretty low because these billing calls are much shorter than these support calls. So the question might be, could I maybe cross-train the support people to do billing and the billing people to do support, and then instead get rid of this caller selection, bring everyone through here, and maybe this will increase my utilization across all of my support representatives, so that I don't have people just sitting idle, so I get more bang for my buck. And then does that actually maybe reduce the waiting time of the callers sitting in the queue? And so I could imagine then taking my system 1, and I run a bunch of replications and they have outputs. Let's say those outputs are, average time in the queue. And then I get a mean for that average time in the queue across those replications and a variance. And then likewise for my hypothetical model, in my simulation, I've got these, again, the average time in the queue for each replication, the average across the replications, and the variance across the replications. Now, the idea here is that I might not get the averages just right to do an absolute estimate. Like it might be coming out of these things that this estimates they wait 5 minutes in the queue and this waits 4 minutes in the queue. But in reality, it's not 5 minutes, more like 10. But if I can be confident that if there is a difference between these in sim, there will be a difference in the real world, then sometimes that is fine, even if the absolute measures aren't calibrated well. So comparing relatively sometimes allows you to get around a lot of the calibration you'd have to do if you're trying to absolutely estimate, a single parameter. So if I really need to estimate what the true average time in the queue is, I've got to make this simulation work exactly at the real world. But if I really just want to know how much better is cross-training these operators so that I get 7 instead of 4 by 3, then in that case, I may not need to calibrate this super well, just so long as I could be pretty confident that if there's a performance difference here, there'll be a performance difference in the real world. So that's one, question. Exactly. The null hypothesis, the question was, is the null hypothesis between these two is that there is no difference? That's right. So the null hypothesis is that these two means, or these two population means, are equal between these two. We want to detect, is there a difference? And then from our data, can we tell which system is better? And so that's what we're doing here. So the idea here is we would like to calculate a confidence interval of the difference. And so we've got system 1, average wait time for system 1, average wait time of system 2. We could subtract those, and we've got kind of then a sample of what the difference would be between the two systems. And then we've got a confidence interval that's associated with that. So it's just the standard error of this mean scaled by that t-value. And that gives me a confidence interval here. So the idea here is for case 1, if this confidence interval of the difference between these systems is significantly negative, so 0 is not included and it's negative, then I'm going to assume that y2 is bigger than y1. So if these are average wait times, then I would say that the wait time in system 2 is greater than the wait time in system 1. And then I would end up, whatever that means. So in this case, that sounds like a bad result. So this would say, system 1 is better than system 2. The other case is this confidence interval of the differences here. So this is a single confidence interval that's summarizing two systems. This confidence interval of the differences might be significantly positive. It does not include 0. Well, that tells me that Y1's score is greater than Y2. So if this is in terms of wait time, it sounds like Y2 is the better system. The third case is that they include 0. In that case, I have no idea if these two systems are the same or different. So that might mean I need to take more data in order to zoom in on the difference. Now, once I get a difference, then I get into the absolute relative thing where I'd say, well, based on these systems, how much can I trust that this relative difference in sim is going to match the predicted relative difference? If I've highly calibrated these, so the sims really do match the real world, then I have to ask, if I were to gather more data to make this a smaller confidence interval so that I can figure out if Y1 or Y2, which one's bigger, is this amount of difference between this confidence interval and 0, if that difference there, is that really worth it for me to go through the reorganization process of implementing this intervention? So that's another sort of separate question. So this is the basic approach that, and I'm going to stop here, that we're going to talk about starting next time, is this idea that we are going to build 2 sample confidence intervals and compare them to 0. And so based on how we design our experiments, we need to put in a different degree of freedom and a different standard error calculation. But then otherwise, across these 3 different ways we run experiments, we analyze them all with the same confidence interval interpretation. All right, so that's all I'm going to do here. Just for kicks, no other attendance exercise. There's just the 2 others that were in the beginning there. And I will see you all Thursday. I'll stick around for a couple minutes if you have any questions. So online, I'm going to stop the recording.